Almost every prey animal on Earth has eyes on the sides of its head. Wide vision, constant awareness, almost no blind spot. A rabbit can see approximately 360 degrees. A deer's field of view reaches around 280 degrees. Hoofed animals of every kind are built to see threat coming from nearly any direction, without turning their heads. Humans gave all of that up. Both of our eyes face directly forward, giving us a binocular field of roughly 120 degrees, and a blind spot behind our heads that is approximately 160 degrees wide. We cannot see what is behind us at all. We traded away more than half of the visual awareness that most animals on Earth consider the baseline minimum for survival. And the question that biologists, primatologists, and evolutionary scientists have been working on for more than a century is, what did we get in exchange that was worth that trade? The answer is not what most people think. And the real story of how human eyes ended up facing forward is stranger, older, and more specific than the popular explanation ever captures. The popular explanation is the predator explanation. Humans have forward-facing eyes because we evolved as hunters, and hunters need binocular depth perception to time and attack on moving prey. It sounds right. Many large predators, cats, dogs, wolves, bears, owls, do have forward-facing eyes, and there is a real correlation between hunting lifestyle and binocular overlap in parts of the animal kingdom. But the predator explanation, applied directly to humans, runs into a serious phylogenetic problem. Humans did not evolve from a predator lineage. The primate family, which includes lemurs, lorises, monkeys, apes, and humans, developed forward-facing eyes millions of years before any tool-using or systematic hunting behavior appeared. The last common ancestor of primates was not a hunter. The forward-facing eyes came first, and they came for a completely different reason. Before going further, it helps to understand exactly what forward-facing eyes actually give you that side-facing eyes cannot. Both eyes facing the same direction means both eyes see the same scene simultaneously. And because each eye is positioned slightly differently, each eye sees that scene from a very slightly different angle. The brain compares those two slightly different images and extracts the disparity between them. And that disparity calculation is the mechanism of stereoscopic depth perception. Stereopsis is the gold standard solution to one specific problem. How far away is that object, precisely, when it is close enough to touch or almost touch? Monocular cues, perspective, shading, familiar size, work for distances measured in meters or tens of meters. But when something is within arm's reach, the only mechanism that can tell you its exact distance to within millimeters is the small difference between your two forward-facing eyes. The forward-facing placement is, in this respect, the anatomical precondition for the kind of high-precision, close-range depth perception that a primate hand requires to do anything useful. The leading scientific explanation for why primates developed this arrangement traces back to a 1974 paper by primatologist Matt Cartmel, and has been built on, revised, and debated for the 50 years since. Cartmel's argument, which has gone through several versions and is still being actively refined, holds that forward-facing eyes evolved in primates because of two intertwined pressures: life in a three-dimensional arboreal environment and the visual demands of catching small, fast-moving insects at close range. The arboreal component is the more widely accepted part. Primates, unlike squirrels or tree shrews or most other arboreal mammals, regularly leap between branches and between tree trunks. A squirrel scurries along surfaces and keeps lateral eyes because it needs panoramic awareness more than it needs precise depth at a specific point. A primate that leaps across a 4-meter gap between tree trunks needs something very different. It needs to know, in milliseconds and with precision measured in centimeters, exactly how far away the landing branch is before it commits to the jump. The margin for error on a 4-meter arboreal leap is not large. The successful leaper, is the one whose visual system can make that depth calculation accurately and fast. Recent biomechanical research, including a 2024 paper by Addison Kemp published in the Journal of Experimental Biology, has strengthened this account by showing that binocular field overlap correlates with leaping behavior across mammals more broadly. Animals that leap tend to have wider binocular overlap. Animals that scurry tend to keep lateral placement. Cartmill also argued, in the insectivore component of his hypothesis, that catching small and fast-moving insects in the cluttered visual environment of a forest understory places additional demands on close-range precision depth perception and hand-eye coordination. A primate hunting insects in low light, among twigs and leaves, needs to localize a small moving target precisely enough to pluck it from a surface. And that task demands the kind of millimeter-accurate depth data that only stereopsis provides. A separate and more recent proposal, put forward by Mark Changizi and colleagues in 2008, adds a third account to the picture, which they call the X-ray vision hypothesis. Changizi's argument is that forward-facing binocular vision gives an animal the ability to see through sparse obstacles, leaves, twigs, clutter, by combining the two slightly offset views from each eye into a composite image that recovers what's behind the obstruction. An animal with side-facing eyes, each seeing a different part of the world, cannot perform this computation. An animal with overlapping forward-facing fields can effectively look through thin clutter, a significant advantage in a densely vegetated forest environment. The X-ray vision account is treated by most researchers not as a replacement for the arboreal leaping and visual predation accounts, but as a complementary selective pressure that reinforce the same anatomical solution. Lynn Isbell's snake detection theory adds yet another layer. Her argument is that the primate visual system, including its sensitivity to sudden movement, evolved partly as a defense against snakes, a major predation risk for small arboreal mammals in forest understories across the world. Forward-facing high-resolution vision, in Isbell's account, supports the rapid detection of a camouflaged snake making a sudden strike, making the forward-facing arrangement an anti-predator adaptation as much as a foraging one. What all of these accounts share, the arboreal leap, the insect catch, the X-ray vision, the snake detection, is that none of them is about hunting large prey. The forward-facing eyes of primates did not evolve to chase down a deer or time, an attack on a running animal. They evolved for the close range, high-precision, three-dimensional visual demands of life in a forest, judging gaps between branches, catching things within arm's reach, seeing through leaves, and detecting sudden movement from a hidden threat. Owls, often cited alongside primates as among the most binocular animals on Earth, evolved their exceptionally wide forward-facing fields completely independently, driven by the demands of hunting from ambush in near darkness, where precise depth data on a moving target is the difference between a successful strike and a miss. Two completely separate evolutionary pressures, in two completely separate lineages, arrived at the same anatomical solution, because the solution was that good at solving the precision depth problem. And the cost, the 160-degree blind spot directly behind the human head, the complete absence of peripheral monitoring in that zone, is a cost we are still paying. The behavioral compensations are built into how we live. Humans have unusually strong neck mobility relative to most mammals, allowing rapid head rotation to survey behind us. We walk in groups rather than alone. We build shelter that limits the angles from which we can be approached unseen. We talk face-to-face rather than side by side. None of these are accidents. They are the downstream consequences of an expensive visual trade made in a forest millions of years ago. We gave up the peripheral awareness of a prey animal. We got the close-range precision depth of something built to navigate a three-dimensional world with its hands. And we have been compensating for what we lost ever since. If you want to understand the other extraordinary sensory trade-offs that shape the human body, the ones that gave us extraordinary capabilities in one direction, while leaving us completely exposed in another. That video is on your screen right now. Imam al-Ghazali in Ihya Ulum al-Din, Ibn al-Qayyim in Madarij al-Salikin, and Ibn Kathir in his Quranic commentary all converge on the same definition. Tawakkul is the state in which the actor has done everything within his power to comply with the command, and has then placed the outcome entirely in the hands of Allah, neither retreating from action nor hedging it with self-protection. Ibrahim, did not minimize the command. He did not negotiate a softer version of it. He took his son, walked to the place of sacrifice, laid him down, and raised the knife. The outcome, the survival of Ismail, was never Ibrahim's to control. And tawakkul, in the classical definition, is precisely the posture of acting fully while releasing the outcome completely. Allah's words at the end of verse 105 and 106 add the final interpretive note. Indeed, this was a clear test, and the scholars read this as confirmation that what made it a test was not the physical act, but the spiritual state that drove the physical act. If you want to go deeper into the life of Ibrahim, the earlier tests, the fire of Nimrod, the building of the Kaaba, that complete story is on your screen right now.